Here in this video you are going to learn about the initial value theorem and final value theorem of Laplace transform. Okay, so initial value theorem means the starting value of x of t. So here we are assuming that the x of t is a causal signal, which means x of t is a right-sided signal. So the minimum value of x of t is x of 0. The first value, not minimum value, the first value of x of t is x of 0. Right, this is called as the initial value. All right, so according to the initial value theorem, it states that if the Laplace transform of x of t is equal to x of s, then x of 0, that is the initial value of x of t, the first value of x of t, then x of 0 is equal to limit as s tends to infinity s into x of s. That means x of 0 is nothing but the value of s into x of s when we substitute s as infinity. See, this is called as the initial value theorem. Okay, so now let's look at the derivation. Alright, so here we know that we are first applying the time differentiation theorem. The time differentiation theorem, right? We know the time differentiation theorem, that is the Laplace transform of dxt by dt is equal to s into x of s minus x of 0. Okay, this is called as a time differentiation theorem. So I'm going to start my property with this theorem. Okay, that is, if I'm applying Laplace transform to the differentiation of dx of t by dt, then I get integral 0 to infinity dx of t by dt into e raised to minus st dt. Okay, this is the Laplace transform of differentiation of x of t, which is nothing but, as you have learned before, it is s into x of s minus x of 0, where this x of 0 is the value of x of t at time t is equal to 0, or also called as the initial value. Okay, taking limit as s tends to infinity, taking this limit on both sides, here and here, taking on both sides, we get limit as s tends to infinity integral 0 to infinity dxt by dt into e raised to minus st dt. Okay, and the limit on the RHS is limit as s tends to infinity s into x of s minus x of 0. Okay, so now in the LHS I'm going to substitute s as infinity. Okay, and if you look very carefully over here, there is s only in this location. This is the only value, this is the only variable that has s. Okay, so if I put s as infinity over here, then this will become e raised to minus infinity. If I put s as infinity, the s is already over here. It's only in this LHS, only over here only there is s. So if I put infinity over here, it becomes e raised to minus infinity, and we all know that e raised to minus infinity is 0. So 0 into entire thing is nothing but 0 itself. So as s tends to infinity, e raised to minus st, this e raised to minus st becomes e raised to minus infinity, which is 0. Therefore this left side equation, left hand side becomes 0. So 0 is equal to limit as s tends to infinity of s of x of s minus x of 0. Okay, this x of 0 has nothing to do with s. This s does not have anywhere over here, you see. So I can take this value outside my bracket. So this limit is applicable only to the first term. It is not applicable to the second term because there is no s over here. So therefore this becomes limit as s tends to infinity s x of s minus x of 0. Okay, and if I put this x of 0 in this side of this equation, then I get x of 0 is equal to limit as s tends to infinity s into x of s. Okay, this is called as the initial value theorem, the theorem that is used for finding the initial value. That means in order to find the initial value, we don't need to find the time domain signal. We can find the initial value of the signal from its Laplace transform itself by simply applying the equation. That is, multiply your Laplace with s and then substitute that s with infinity. Okay, now next we will look on to the final value theorem. Okay, it's the opposite of initial value theorem. All right, so we know that the last value of x of t, since x of t is a right-sided signal, the last value of x of t is x of positive infinity. This is the last value, or also called as the final value of x of t. Okay, so in order to find the final value of x of t, we can also find, just like before, we can also find it in the using Laplace theorem. If Laplace of x of t is equal to x of s, then the final value of x of t, that is x of infinity, is equal to limit as s tends to 0 of s into x of s. That means all you need to do is multiply your Laplace transform with s and then substitute that every s over there with 0. That's how we can get the final value of x of t. Okay, so let's see the derivation. The derivation here also, the derivation just like the previous initial value theorem, here also the derivation starts with the time differentiation theorem. That is Laplace of dxt by dt is equal to s into x of s minus x of 0. Okay, here x of 0 is the initial value, s into x of s. Alright. So now what I'm going to do is I'm going to apply my Laplace transform to this equation, right? This is Laplace of, that means you have to multiply this with e raised to minus st and then integrate it with 0 to infinity. So you get integral 0 to infinity dxt by dt into e raised to minus st dt is equal to RHS, s into x of s minus x of 0. Okay, now just like before, now I'm going to apply limit on both sides for s tends to 0. So therefore applying limit as s tends to 0 on both sides, here and here. So I get limit as s tends to 0 of integral 0 to infinity dxt by dt into e raised to minus st dt. Okay, is equal to, now I'm applying limit over here also, so it becomes limit as s tends to 0 s into x of s minus x of 0. Okay, now I'm going to, if I apply s or s is equal to 0, so I limit s tends to 0, right? So if I apply s is equal to 0 here, s, if you look at this side, look at this equation, s exists only over here. This is the only place that has s. So if I put s is equal to 0 over here, this will become e raised to 0. E raised to 0 is 1. So therefore this becomes 1 over here. Okay, so integral 0 to infinity dxt by dt of x of t into 1 dt, okay, is equal to limit as s tends to 0 x of s minus x of 0. Here also, like before, here here this limit has nothing to do with x of 0 because there is no s over here. So I can take this x of 0 outside. So this will become limit as s tends to 0 of x of s minus x of 0. Okay, so now here if you look carefully, I'm doing nothing but applying integration to a differentiation. You see, integration is with respect to dt and differentiation is also with respect to dt. This is nothing but the opposite of each other, right? Integration of a differentiation is nothing but of that signal is nothing but the signal itself. Okay, so I get x of t itself over here, right? Because these two operations are cancelling each other. They will cancel each other, right? So integration of a differentiation is that signal itself. So x of t, and the limit is from 0 to infinity. So 0 to infinity, x of t 0 to infinity is equal to limit as s tends to 0 s x of s minus x of 0. Okay, so now if I'm applying the two limits inside my signal, I will get x of infinity minus x of 0 is equal to limit as s tends to 0 of s x of s minus x of 0. Okay, so now what I'm going to need to do is I can simply cancel these two signals. X of 0 and x of 0 gets cancelled. So at the end I get my x of infinity is equal to limit as s tends to 0 of s into x of s. This means that in order to find the final value of x of infinity, we don't need to find x of t, right? You can, looking at the Laplace transform also, I can also find the final value. How? By simply multiplying my x of s with s and then substituting every s in that equation with 0. Okay, so now let's do some problems. Find the initial and final values of the signal. This is the first question. That is, x of s is equal to s plus 4 by s square plus 3s plus 5. Okay, so here given x of s is equal to s plus 4 by s square plus 3s plus 5. Okay, so first I'm going to find my initial value. Alright, initial value, we know that x of 0 is equal to limit, So if it is initial value theorem, then I have to apply limit s tends to infinity. If it is a final value theorem, that is x of infinity, then I have to apply limit as s tends to 0. You can remember like that, opposite effect. Okay. So x of 0 is equal to limit as s tends to infinity s into x of s. S into x of s. Okay. S into x of s. Here x of s is given, so I'm going to substitute that over here. It will become limit as s tends to infinity of s into s plus 4 by s square plus 3s plus 5. Okay. Now if you look very careful over here, if I simply apply infinity over here, this will become infinity into infinity plus 4 divided by infinity, which is not a proper value. Okay, so what I'm going to do is I'm going to make a small modification to this problem in such a way that I will get a proper value. Okay, and for these kind of questions, one way for infinity, if you are going to apply s tends to infinity, we know that any number divided by infinity is 0, right? So I'm going to try my best to make every term that you see here, every value that you see here, divide by infinity, because any value divided by infinity is 0. Then after that I apply my s as infinity. So here, in order to remove this s, I can't make this s over here. If we can't remove anything, if you can't do anything, then you cannot find the initial value. Okay, so I have to remove this s over here. Okay, I have to remove all this s over here, and I need an s over, and this 4 can also have a 4 by s. I can make sure that also can happen, so that becomes infinity, or that becomes 0. So in that case, I can say that limit as s tends to infinity, s into, let me take s common over here, this will become s of s into 1 plus 4 by s. You see, so here 4 by s, so when s becomes infinity, because 4 by infinity, so this will become 0, right? Divided by, here also, here what I can do is I can take s square as outside, right? I can take s square common over here, because if I take s square common over here, then this s into s by s square will get cancelled, right? So I'll take s square common. So what do you think I will get? 1 plus 3s by s square, which is nothing but 3 by s, plus 5 by s square. See, this is how we do the problem. Usually for s tends to infinity, we tend to take the s factor outside, and we tend to make them both cancel each other, so that we are converting every term with s plus 4 and make s as the reciprocal. We bring this s into the denominator side. Okay, so that when I apply infinity to the denominator side, then anything by the infinity becomes 0. So this will become, so this s and s square gets cancelled. See, this is s into s by s square, so these two will get cancelled, and if I put infinity over here, I will get 1 plus 0 by 1 plus 3 by infinity is 0, plus 5 by infinity is also 0. So the final answer is 1. Okay, this is how we find the initial value theorem. Likewise, now let us find the final value theorem. Okay, also x of infinity, final value theorem, is limit as s tends to 0, s into x of s, limit as s tends to 0, s into here s plus 4 by s square plus 3s plus 5. Okay, here also, if I try my best to remove this s, okay, by looking at the denominator, I can see that if I can remove this s, then I can cancel each other, then I can simply substitute the value of s as 0. Okay, so if I get, so here if you can see anywhere, however I try to remove this s, it will always get backfired. I will not get the correct value. So that means the only value that I am ever going to get, no matter how much you ever try, you cannot ever make any kind of modification, or you will always end up having the same value, right? In other words, you will get over here as nothing but 0 into 0 plus 4 by 0 plus 0 plus 5, which is nothing but 0 by 5, which is nothing but 0. Okay. So this is how we do the problem. We'll see if there's any possibility of not getting infinity or 0, or if you are able to get a proper value. Okay. Let's do the next question. Verify the initial value theorem of the signal. These two questions of the signal x of t is equal to 4 minus 2 into e raised to 3t. Okay, so here they ask us to verify. Verify means you have to cross check your answer. Okay, so here in the first question, given x of t is equal to 4 minus 2 into e raised to 3t. Okay, so if I want to find the initial value of t, initial value of x of t, that is x of 0 is nothing but, just substitute t is equal to 0. Right, that's the called as the initial value. So this will become 4 minus 2 into e raised to 0, which is nothing but 4 minus 2, which is nothing but 2. This is the initial value theorem. Okay, and now I'll go to find my I'll find my final value theorem also. Then I'll apply the property and see if they are correct or not. Okay, so likewise, if I find no need to find final value theorem. Only initial value theorem is required for this question. Okay, so now let me apply my initial value property. That is, x of 0 is equal to limit as s tends to infinity s into x of s. Okay, so limit as s tends to infinity s into, so what is the x of s of x of t? It is 4 by s minus 2 by s minus 3. Okay, 2 into s minus 3. Okay, so now I'm going to multiply this s inside this bracket. So that's how I can remove this s over here, and I can see if I could do something over here also. So here, if I multiply s over here, this will become s into 4 by s, which is 4 minus 2 into s by s minus 3. Okay, so now here if I want to disappear this s, if I want to remove this s, maybe I can take s common over here, right? I can take s common over here, so it will become 4 minus 2s by s into 1 minus 3 by s. This is okay. See, so this becomes 3 by infinity, right? This becomes 3 by infinity. 3 by infinity, which is 0, right? So I will get s, I'll write it again. So this will become limit as s tends to infinity, 4 minus s and s cancel, it will be 2 by 1 minus 3 by s. Okay, which is nothing but 4 minus 2, which is equal to 2. That's the answer you got before. Okay, so it is verified, right? Initial value theorem is verified. Now let's look at the second question. Here, x of t is equal to 3 into e raised to minus 5t. Okay, this is the given question. So from here I can immediately write what is my x of s, right? X of s is equal to 3 by s plus 5. See, 3 by s plus 5. Now, so let me check, well, let me apply t is equal to 0 over here. So I will get x of 0 is equal to 3 into e raised to 0, which is equal to 3. Okay, so now I'm going to, let me apply my initial value theorem over here. Let me see what I get. X of 0 is equal to limit as s tends to infinity s into x of s. Here limit as s tends to infinity into s into 3 by s plus 5. Okay, so in order to remove this s, I can take s common at the denominator, so that I can easily cancel each other out, leaving nothing but s by infinity. So here this becomes limit s tends to infinity, 3s by s into 1 plus 5 by s. S and s cancelled. So this will become 3 by 1 plus 5 by infinity. 5 by infinity is 0. So it will become 3 by 1 plus 0, which is nothing but 3. Therefore, Therefore initial value theorem is verified. Okay, let's do the last question. Verify the final value theorem of this equation. X of t is equal to 7 into 1 minus e raised to minus 2t. So here let me first find my final value theorem from the time domain signal. So x of infinity is nothing but 7 into 1 minus e raised to, if I put t is infinity, this will become e raised to minus infinity. E raised to minus infinity is 0. So it becomes 7 minus 1 minus 0, which is equal to 7. Okay, this is my x of infinity. Now let's see if after applying final value theory whether I get the same answer. Okay, so applying final value theorem, comma, I get x of infinity is equal to limit. So if it is infinity over here, then it is 0 over here, s into x of s. Okay, so this becomes limit as s tends to 0, s into here x of s. So what is x of s over here? X of s over here, x of t is 7 into 1 minus e raised to minus 2t, right? So therefore x of s is nothing but 7 into Laplace of 1 is 1 by s minus Laplace of e raised to minus 2t is 1 by s plus 2. So this will become into 7 into 1 by s minus 1 by s plus 2. Okay, or this is nothing but 7 into s into 1 by s limit. I have to apply limit also. I keep forgetting that. Limit as s tends to 0. Okay, limit as s tends to 0, s into 1 by s minus 1 by s plus 2. Okay, so now I'm going to multiply s inside my bracket. So this will become 7 into limit as s tends to 0. So it will become 1 minus s by s plus 2. So now you can see, if I simply apply 0 over here, it becomes 0. So 0, 0 plus 2. No matter however I try, I cannot remove this s over here, right? No matter what magic I do, I cannot remove this s over here. So here it's nothing but, if I'm applying s is 0, this will become 7 into 1 minus 0, which is equal to 7 itself. Okay, therefore the final value theorem is verified. Okay.